So last week we started our unit on astronomy, and we started by talking about some of the components of the universe, some of the things that make up the universe. So let's start with our own solar system. Right? In our solar system, we have the sun at the center. It's providing the light and the energy that allows life to exist on Earth. And it's also creating this very large gravitational field, which causes the planets to orbit around it. Right? We then have a bunch of different planets. Those planets have moons. Smaller things like comets, asteroids are present. And all of that's within our solar system. And the space between these things, right, the space between the planets is a vacuum that contains essentially nothing. Now, if we look a bit further, right, if you have a collection of millions of solar systems, you now have something called a galaxy. Right? And Earth belongs to the Milky Way galaxy. And at the center of each, or at least the center of the large galaxies, is a black hole. And that causes the different solar systems to orbit around that black hole. And then you can start looking out even further and look at these clusters of galaxies, these superclusters, and you eventually have the observable universe. Today, what we're going to talk about is where did the universe come from? And what evidence do we have? What scientific measurements do we have that tell us what the universe is and where it came from? And then also, how did the solar system form? How did our sun and our planets form? So for a very long time, people have been asking, how big is the universe, right? As soon as we started looking out there and seeing that there were other things, well, how far does it go? And it's really only been in the last century, the last 100 years, that astronomers developed telescopes that are able to help us answering that question. Before that, we didn't have the technology to develop large enough and sophisticated enough telescopes. We now have telescopes in space. And those ones are actually even better because they avoid the atmosphere, right? They avoid that layer of air that's surrounding Earth. So the Hubble Space Telescope is a very famous telescope that's orbiting Earth, and if you take out that layer of air, you can get a much clearer image. You can look even further out there. So that telescope is named after Edwin Hubble. So in 1920, he first discovered that stars existed outside the Milky Way galaxy. So before then, we thought that our galaxy was the only thing. We couldn't see beyond that. And in 1920, he discovered that, yes, there are stars beyond that. And in fact, there are millions of other galaxies. So we suddenly realized, hold on, the universe is much, much larger than we ever thought. But that wasn't even his biggest discovery. In late 1920s, he started looking at the patterns of lights that were coming from galaxies. And he found out that each galaxy was emitting a unique colors, or we call them frequencies of light. So if you see a certain color, it's actually because the light has a certain frequency. It's moving back and forth at a certain rate, and that's what gives it that color. And if you measure that with scientific equipment, you can actually measure it right down to a very specific number. We would say it's a nanometer frequency of light. And you can use that to describe very, very small differences between different colors. So what he did is he looked at the light coming from different galaxies, and he realized that each one had very specific frequencies of light that were coming in. But some of them were kind of recognizable. So some of them would be the same frequencies of lights that were coming in, but they were shifted a little bit. So he also noticed that the frequencies were red shifted, meaning that whatever light he was looking at, it was actually shifted a little bit to the right of what he would expect. And he would notice sometimes it was a really complicated pattern with maybe 20 different lines, and that exact pattern would show up, but it would show up shifted a little bit to the right. So he would realize, well, it's the same pattern I'm getting, but yet it's moved. And the only reason that would happen would be if the object was moving away from Earth. So let's say this was your frequency of light. Light's traveling as a wave. If that galaxy was moving away from Earth, sorry, the light's going to be coming back towards Earth. If that galaxy was moving away from Earth, well, that light coming back would now be traveling at a bit of a different frequency because it'd be more spread out here, right? The galaxy's moving that way, but it's going in the opposite direction. So that frequency would be a little bit lower, and we would now see light that's slightly more red. So we call that redshifted. Now he noticed that when he looked at galaxies that were further away, they were redshifted even more. So the closer ones were only a little bit redshifted, the far ones were much more redshifted. So that told him, well, the galaxies have to be moving away from each other, from Earth, and if you look out further and they're more redshifted, they have to be moving away from each other as well. So that told him that the universe is expanding. The galaxies are moving away from each other. So you can think of it like this. This is kind of a example that's commonly used. Let's say you have an elastic band, and these ants are different galaxies. If you took that elastic band and you stretched it, those ants would move away from each other, right? But in this case, it's not that they're moving away from each other, it's that the space in between them is expanding, right? The space in between these two galaxies has expanded, and same thing here. So it isn't that there's some center point of the universe, it's that the space between all of the galaxies is just getting bigger and bigger. All right, so that led to a very important theory. And we have lots of evidence to back up this theory, called the Big Bang theory. All right, so we now know that the universe was created about 14 billion years ago. And there was a hot and dense expansion called the Big Bang. Everything in the universe, including space, time, every planet, every star, every person on the Earth, everything on the Earth, the entire Earth, all of those things were created during the Big Bang or after the Big Bang. So everything in the universe existed at a single fixed point that was very hot and dense. And then suddenly that mass expanded. And at the beginning, there was only simple atoms. So for example, hydrogen and helium were some of the first atoms that formed. And then a billion years later, the first stars, galaxies, and planets began forming. Those different atoms collected together and they got hot enough and dense enough that they could form into larger atoms. And suddenly you had all of these galaxies, stars, and planets forming. The heat and pressure at the center of stars created larger atoms like carbon, oxygen, and iron. So at first this theory seems crazy. I mean, so the universe just came out of nothing? It just appeared from this hot, dense point? Yes. And what is the scientific evidence that backs that up? Well, let's look at some of the most important ones or the most common ones. All right, first thing. Biggest piece of evidence is the redshifting of light. We know that the galaxies are moving away from each other. We know that the universe is still expanding. We know that gravity pulls things back together. So why is it still expanding? Well, there must have been some initial burst of energy that caused them to move away from each other and continue to overcome gravity to continue moving away from each other. So there must have been some sort of event at the beginning of the universe that released that energy. The other evidence that came later, I think it was in the 1960s, was background radiation. So we know what kind of radiation would be created in a Big Bang type of event, and that radiation still exists today. And some of it is still reaching us today. And if we measure that, it matches up with the models that we have for the Big Bang. So those are the two big pieces of evidence, but there are many other things that have been looked at. So for example, ratios of helium and the evolution and distribution of different galaxies. So there's many pieces of evidence, but these are kind of the main two. So this really is a very accepted and solid theory. So the next question is, well, how was our solar system formed? All right, so after the Big Bang, we started getting hydrogen and helium atoms. The universe expanded, and you ended up with these giant clouds of dust and gases. And eventually, those things started forming together. So our solar system formed about 4.5 billion years ago. And it started from a dense cloud of interstellar gas and dust. Interstellar just meaning somewhere between other stars, right? Somewhere between other solar systems. Uh, you had this giant cloud of gas and dust, probably mostly hydrogen. And eventually, that cloud collapsed in on itself. Gravity pulls things together. And eventually, gravity pulled that gas and dust into a hot spinning disk, right? So you end up with this cloud of interstellar gas cloud, and eventually it pulls together into this spinning disk. As more and more gas and dust gets pulled in, the pressure and the heat increases in the middle. And the pressure became so great that the hydrogen atoms started to combine together. They combined together to give you helium. And when that started happening, our sun was born. Our sun is a chemical reaction between hydrogen and helium. So in this case, that's how our sun was created, just from the pressure and the heat of a cloud of spinning dust and gas. Some of the matter that was further out on the disk, on the outside, some of that started to combine together. And it clumped together, and eventually some of those pieces grew large enough that they had enough gravity to start pulling other things in, and they formed into spheres. And that was the formation of our planets and our moons. And that was the formation of our solar system. And Earth just got really lucky, right? Earth got lucky that it was close enough to the sun to be warm enough for life, and not too close that it was too hot. And it was lucky enough that eventually water was able to exist in a liquid form, which allowed life to exist. So we call that region that could support life, that could support liquid water, is called the Goldilocks zone. So when we're looking at distant galaxies, we're always looking for that Goldilocks zone. We're looking for planets that exist a perfect distance from their suns, that they could have liquid water and possibly life. So one of the famous questions that's asked here is, well, where did the atoms that I am made from come from? I know that my body is mostly, well, hydrogen, oxygen from the water, and carbon. Those are the main things that make up my body. Hydrogen, oxygen, and carbon. Where did those things come from? Well, most of them came from a star. Hydrogen and helium were produced in the early stages of the universe, but almost all of the other elements on the periodic table, almost all of those other elements were created in a distant star, and most likely billions of years ago. So our sun is big enough that it can create anything in the periodic table up to oxygen. But anything larger than that, any larger elements would have had to come from a bigger star. And bigger stars they have more pressure and more heat, so they can actually create larger atoms. So for example, all of the iron that's on Earth, well, it couldn't have been produced in our sun. It's not big enough or dense enough. So all of the iron on Earth had to have come from some distant star billions of years ago. There was enough density and heat that it was able to squish atoms together to form iron. And that iron perhaps traveled here in a meteorite, or perhaps traveled here, or perhaps was here in this large interstellar dust cloud. So what are you made of? Essentially stardust, the remnants of the density and heat at the center of a distant star.